All right, guys. We know you guys may have already reviewed this stuff. Braden and I, we're going to cover the first two chapters that we talked about in Chem 106 this semester. We did reviews on these originally, but unfortunately we weren't able to video them, so they're not posted. So we just wanted to go through a few of the main concepts that we covered in these chapters, just so you guys can remember and start thinking about what we did. It feels like a long time ago, a few months ago. So the first thing we talked about in chapter 13, one of the main concepts was vapor pressure. And I just want to explain real quickly to remind you guys what vapor pressure is. Vapor pressure is the pressure of a gas above a solution. So if you can imagine, we have a closed container right here, and we have some liquid in there, and there's going to be some gas above that liquid. The vapor pressure is the pressure of that gas above the liquid. So there's a few different things that can affect are different factors that affect vapor pressure. Number one being intermolecular forces. And you guys remember, intermolecular forces are forces between different molecules. And one of the main ones that we focus on when we talk about vapor pressure is hydrogen bonding. Hydrogen bonding is when molecules are able to form hydrogen bonds with each other, and those hydrogen bonds are able to strengthen the liquid as a whole. They're able to hold those molecules in the liquid tighter. So what we see is if we have a lot of hydrogen bonding and we have a lot of high intermolecular forces in our solution, then it will actually be harder for those molecules to be jumped into the vapor phase. So if we were going to add energy, add heat into that solution, if those molecules are held together tighter, they're going to have a harder time jumping into the gas phase. The second thing that affects vapor pressure is our temperature. And this is simply because as we heat molecules up, they become more excited, and if they get enough kinetic energy, they can eventually bust into the gas phase from the liquid phase. And the last thing is surface area. Surface area is pretty self-explanatory. If you can imagine, we had a container this big and a container this big. If we had a container this big, there would be more molecules would be able to get to the surface of that liquid. And then if we started heating that up, or if it was just naturally evaporating, more molecules would be able to evaporate into the gas phase simply because there's more on the surface of that liquid. And when more molecules are entering the gas phase, that's going to increase our vapor pressure. So now I just want to do a couple examples of vapor pressure and how it's affected by our intermolecular forces that we talked about. So I drew three molecules on the board right here, and I just want to go through and compare each one, and we're going to figure out which one is going to have the highest and which one's going to have the lowest vapor pressure. So the first one is an ether. An ether is simply an oxygen that's doubly bounded by two carbon chains. The second one is an ethanol, which is just an alcohol. It's a carbon chain with one hydroxy group on the end. And our last one is water, as you guys know, is H2O. So let's talk about water first. Water has two hydrogens on it, as you can see. So water is a great hydrogen bonder because it's able to hydrogen bond in two places on the same molecule. Ethanol, in contrast, only has one H on it, and so it can only hydrogen bond in one place. The alcohol still will hydrogen bond pretty well, but not as good as water. And lastly, the ether, as you can see, there's no H on the ether, and so there's not going to be any hydrogen bonding going on with that. So let's go ahead and rank these in increasing vapor pressure. So number one, like we said, water can hydrogen bond in two places. So if we have a solution of pure water, it's going to be pretty tight hydrogen bonded. And so water is going to have our lowest vapor pressure because it's going to be harder to get those molecules into the gas phase. Our second would be ethanol because it's not as good of a hydrogen bonder as water, but it still will hydrogen bond. And so that would be number two in our increasing vapor pressure. And thirdly, our ether would have the highest vapor pressure because it has the lowest intermolecular forces. It won't hydrogen bond like ethanol and water, and so therefore those molecules will easily break into the gas phase from the liquid phase. One of the other things we talked about when we talked about vapor pressure in this chapter was Raoult's law. And what Raoult's law tells us is if we have a solution with different gases dissolved in it, we can actually figure out through the partial pressures and the mole fraction of the gases what that total vapor pressure in our closed container is. So pretend we had nitrogen gas dissolved, oxygen, hydrogen, these different gases. what we can do is find the vapor pressure of those gases purely and multiply that times the mole fraction. And then what you're going to do is add each one up. So you do this for hydrogen, you do that for nitrogen, oxygen. You sum all those up, and that's going to give you your total vapor pressure above that solution. Okay, switching gears. Next we started talking about how salts dissolved in solutions can affect the properties of the solution. So one thing we talked about was freezing point depression and boiling point elevation. And this had to do with, if you guys remember, the Van't Hoff factor. The Van't Hoff factor, this I right here, comes with, if we talk about salts, how many ions will form. So for example, let's say I was going to dissolve calcium chloride in water. Calcium chloride is a strong electrolyte, so it will completely dissociate in water. And so how many ions would be formed here? There would be 1 calcium ion and 2 chloride ions. So when we use these different equations, our Van't Hoff factor, again, is the number of ions formed. So for this particular example, it would be 3. The Kf and the Kb in the equation are just constants given for that specific salt that you're dissolving in the solution. And the m, again, notice here, this is a lowercase m, it's molality. It's not molarity. And molality is your moles of solute divided by the kilograms of solvent. And these equations are really simple to use. The type of question that I could foresee Dr. Macedoni saying is, you have sodium chloride or calcium chloride and you dissolve it in water, how is the boiling point going to be affected? And basically all you do, you find the Van't Hoff factor, the Kb will be given, you find the molality, it's just a plug and chug. Should be really simple to get those points on the final. Okay, I think that's pretty much it that I had, so I'm going to pass it over to Braden.
Okay, you guys, so we're going to shift gears and talk about rate laws and kind of go through the most important things you need to understand. So unfortunately, we can't cover everything that could potentially be asked, but we're going to cover the majority of the things that are probably the major topics and the things you should definitely understand in order to really kill this part on your final. So number one, when we're talking about rate laws, we have to understand, well, what does that mean? Lately, we've been going over a lot of stuff like equilibrium, acids and bases, which deal with this K constant, and also with this products over reactants expression that we've been using a lot. We need to shift gears and kind of push that to the side and understand that rate law, we're not dealing with a ratio of products over reactants, but rather we're only worried about our reactants. Because in a rate, what determines how fast a reaction occurs is just how quickly can both of the reactants come together, react to form a product. So really, we don't deal with our products. So make sure you understand that, and as you're solving problems for this, you're only looking at reactants and how that's affected. So a lot of the questions that could be asked is to write a rate law. Going over the basis of a rate law really quickly, here is an example of a rate law. A rate law will always be the rate, or how fast the reaction is occurring, and the units for rate will always be molarity per second. So keep that in mind when you're solving problems. That will be equal to some K constant, right? Some rate constant, times the concentration of your reactant, that's why I have R here, raised to the order that, the order that this reactant affects the rate. So what exponent does this reactant affect the rate? And we'll get into a problem that deals with that. Notice I just used one concentration of a reactant, but you can have several different reactants. So know that it's not just one concentration of something, but it could be several. We'll get into problems of that. That should just be a review of what a rate law looks like. So there's going to be several things that affect rates, 4 things specifically that you need to know. And those 4 things I have here are a little bit abbreviated. Temperature will affect how fast my rate will go. Also, concentration of my reactants. If I up my concentration, this is a direct relationship here. If this number gets bigger, then the rate will also get faster. So concentration will affect that. Physical state, so whether I'm a gas, a liquid, or a solid, will really, what this means is, how can I use the collision theory and how can different reactants hit together to actually react, and that will be largely dictated whether or not they're solids, liquids, or gases, and how much they can orient themselves and things like that. Catalyst, so anything that, you guys understand what this means, just any substance that's going to speed up my reaction. So any catalyst will obviously change the rate of the reaction. There's going to be several equations that you're going to need to know. Those equations are listed really neatly in a table that we created in class, and in that table we'll see first, second order, zero order, and all of the equations you need to know. What I think we want to highlight in this video is understanding if you're given data about a rate, or you're given data about a reaction, and you understand the rate law, and you know which order the rate law is, you can try to figure out, or if you don't know which order the rate law is, you can try to figure that out by graphing a little bit of data. So hopefully this is just a reminder for you, but if you are given a bunch of different reactants, right, or different concentrations of your reactant, if you take the natural log of the different concentrations at different experiments, for your y-coordinate here, and for your x-coordinate, you take the time, or the different times that those reactants, that concentration that reactant was at. If you graph those values and you get a straight line here for the natural log of your concentration of your reactant, that is a first order reaction. Same thing with second order here. If you take 1 over the concentration of your reactant here, then that will cause you to be second order. So be practicing problems like this, be able to recognize when you get a straight line or your graph becomes linear, that will dictate if you're first or second order, depending on this part right here, your y-axis. So that's really important. Make sure you look that over, and make sure you also understand these 4 things. So let's shift gears and actually do a problem over here. So hopefully you guys can see this chalk okay. This board's just a little bit different color green, so the chalk shows up a little bit faint. But what we have here is an experiment. This is my exact reaction. Okay, I've got the phases, what's going on, my 2 reactants. Again, this is rate law, so I'm only worried about my reactants. So that's why I have the concentrations of each reactant at each different experiment that I did. Over here I have the specific rate, or how quickly that experiment occurred, and that magnitude of those numbers right there. So now I have to determine, okay, what is the rate law, or how can I write the rate law? And I really need to determine what is the order for each reactant species individually. Is it good?
Yeah, that's good.
Okay. So number 1, the best way to do this is to look at each experiment and choose experiments where one of the reactants here, either NO or H2 here, where we kept the concentration the same. So we can look specifically at how did the other reactant affect the rate. So the first thing we see here is that we kept the concentration same for experiment 1 and 2 for NO, and we can look at how the concentration specifically of H2 affected the rate. So I noticed that I doubled my concentration of H2 while I kept this the same. I look at my rate here and I notice that the rate also doubled. So that is a 1-to-1 ratio. When this doubled, all this did was double as well. So that means that my order for H2 specifically should just be 1. So an exponent of 1. And oftentimes all the time, we don't write that 1. It's just assumed if you don't have anything else. Okay, so we know what this is going to be for H2. Now let's look for NO here. If we pick an experiment where we kept the concentration of H2 the same, clearly right here at the end, we kept the concentration at 18 molar, or whatever it was, whatever our measurement was. And what did we do with NO? We also doubled it. So when we doubled the concentration of NO here, what happened to our rate? It quadrupled. So we doubled this and we quadrupled that. That means our exponent is 2 there. So we're squaring that. So if we want to write our rate law, now we're ready. We know that the rate of our reaction is determined by the K constant. We'll talk just a minute about that in just a second. Times the concentration of H2. The exponent for H2 was 1. Times, that was ugly. Times the concentration of NO. We know that that was squared. So a question that could be asked, if you're given the rate law, this is the correct rate law. What is the overall rate order? Or what is the order of the overall reaction? All we do is sum up the exponents here. So the overall order of this reaction is 3. One thing to not miss on these problems as well, you guys, and we've talked about this before, this isn't technically all the way correct. This isn't wrong, but to make this all the way correct, or if we wanted to write a full rate law, we could actually solve for what this K constant is now, an actual number, and we can determine what the units are because we can see what the units would have to be because we know that this is now a third order reaction. So what you'll need to do when you're actually solving for these is plug in real numbers. The rate here, we have that number here, and concentrations here, and we know the exponents, we can just solve directly for K and actually put a number in when you write a rate law. So let's talk about understanding the units for this really quickly. We talked about over there, the units for a rate will always be molarity per second. And that was what it will always be. So we remember that this was concentration, right, in molarity. This was concentration in molarity. So when we multiply these two together, this one squared multiplied by this one, overall in our numerator, we got molarity cubed. So the units for our K need to be something that will cancel out at least two of these, right? So that overall we get molarity per second. So the units for our K, so units of K equal molarity minus 2 S minus 1, right? So we know that that is to be able to cancel out two of these and put seconds in the denominator here. So review these types of things. We've talked about this a lot. We've done practice problems with this and understanding the constant of our K. So the units of our K tell us a lot about the order and everything. So this is the rate law, remembering to actually solve for a real number for this and include the units. So now let's talk about this right here. This is also dealing with rate laws. We talked a lot about mechanisms and different reactions. We know that some reactions are what we call elementary steps. And what elementary step means is if I say that A comes with B to give me C, I'm literally saying this reacted directly with this to form that. That's elementary, meaning there aren't separate or intermediate little reactions occurring to actually give me this total. It was literally this reacted directly with B to give me C. So a lot of times we're given reactions like this reaction right here. We know that this reaction isn't actually two NOs react directly with two H2s to form these products. It's a little different than that. They told us that there is a mechanism associated with this overall reaction to actually do this, the way we write it. It actually has to occur like this. So these are what these mechanisms are. Now each one of the steps of a mechanism is an elementary step. It's exactly this. So in order to write a rate law for a mechanism, we know that you're only as fast as your slowest step. A lot of times we would say in our reviews, you're only as good as your worst player, things like that. So it's the same type of idea. We're only as fast as our slowest step. So to write a rate law here, we only worry about our slow step. So I look at, this is my slow step right in the middle. I need to write a rate law coming directly off of this line here. So one thing we've talked about a lot, and you guys are noticing right now, oh no, there is an intermediate. And what an intermediate is in the step 1, I formed N2O2, and I immediately am using N2O2 as a reactant to form these things. So N2O2 is being made and immediately used. And a substance that's being made and immediately used, I can't actually measure the concentration of that because it's made and gone so quickly, so I can't include it in a rate law. So I have to use something else that N2O2 is equal to or equivalent with when I write my rate law. So no, this is my intermediate, this is bad. I got to change this. I can't just write N2O2 in my rate law. So how I do that is I look at the above equation where it was made, and I set the two rate laws equal to one another. So I know that the rate law for this is rate is equal to K1 forward times NO squared. And that's equal to the rate of the reverse, which is K reciprocal of 1, times the concentration of N2O2. That is the expression for the above thing, and that is also equal to the rate. So if I wanted to solve for what this is directly equal to, I just need to divide by K reciprocal of 1. So I know that N2O2, the concentration of that, is equal to K1 divided by K reciprocal 1 times the concentration of NO squared. Right? This concentration is directly equal to that. And we got that from this first line and solving it like this. So I come down here and I replace this now. This whole piece, I can erase this because I don't want to use that exact thing, and I say, okay, that was equal to K1 divided by K reciprocal of 1 and the concentration of NO squared. Okay, this is perfect. So now I have the concentration of this, what that used to be, plus that, gives me my rate law. So when writing my rate, I say, okay, my rate is equal to a k constant. Well, it's not just going to be any k constant, it'll be k2 times k1, coming right here, divided by k reciprocal of 1, because I'm just adding these two reactants together, times NO squared times H2. Okay, times H2. So this is my rate law. And we've told you before that if you don't want to write this really, really messy K's for the overall rate law, feel free to just write K and put K new, but off to the side you could write K is equal to this. And with your multiple choice exam, you're not going to have to write anything like that like you would on a free response. But just be looking for things like that. So this is how we solve for the rate law of a mechanism. Understanding it comes directly from our slow step, and that is really all we're worried about. So these are the main problems you're going to have to do. You're going to have to solve for the rate law. You're going to have to write the correct rate law, potentially solve for a different concentration. Again, I said earlier in the video that there are several equations that you need to make sure you know, and it's all in this neat table that Dr. Macedonia has made. So it's useless for us to just write them all on the board because you have them even clearer and better in a really neat form in your notes. And if you didn't write those down during class, it's actually in the slides and it's really crisp and good. So make sure you understand just how to plug in raw numbers into those simple equations, as long as you know to use the first order or the second order equation. A little tidbit from radioactivity: all radioactivity is a first order type rate, so make sure you use always first order equations. That should be everything for rates, and good luck in your guys' exam.